sound is on. That's good to hear. I've recorded entire lectures without the sound on. It's not great. Okay, so we're on lecture 1.4, Thevenin's and Norton's theorems. So we're probably getting into some stuff that you guys haven't seen before. Maybe some of you have seen it. If so, that's awesome. Thevenin's and Norton's theorems yield ways to simplify our models of circuits. Okay, so we're going to take a complicated circuit and make it simpler. And we lose some information when we do that, but we still retain some. And so that's what these theorems state. So Thevenin's theorem says the following remarkable theorem has been proved. Thevenin's theorem says, given a linear network of voltage sources, current sources, and resistors, so those are like all the circuits we can imagine so far, right? Those are the only components we've got. Voltage sources, current sources, and resistors. So given that, the behavior at the network's output terminals can be reproduced exactly by a single voltage source with voltage VE in series with a resistor RE. Okay? So that's a kind of a remarkable idea that you could have like thousands of sources and resistors, and you could boil it all down to, at the output terminals, you could boil it all down to one voltage source or current source and one resistor. Okay? So, Thevenin's theorem says specifically voltage source. Now the question is, what are these magical two values, VE and RE? What is this equivalent voltage source, and what is this equivalent resistance? That's the question we've got. So, determining RE. It actually doesn't matter which one you do first. You can find RE or VE first. It's typical to start with RE because it tends to be a little easier. So I think a lot of people go with that. So let's just do that. So the equivalent resistance, RE, of a circuit is the resistance between the output terminals with all input terminals or all inputs set to 0. Okay? So you set all of the inputs or the sources to 0, and then you find what the resistance is between the output terminals. Setting a voltage source to 0 means the voltage on both its terminals are equal, which is equivalent to treating it as a short or a wire, right? So if you want to set a voltage source to 0, you just replace it with a short, okay, which is with a wire. If you want to set a current source to 0, then we have to have 0 current flowing through, which is equivalent to having an open circuit. So you just take those out and replace it with nothing. Okay? Determining VE. So we know RE now. RE is pretty straightforward. Now VE, the equivalent voltage source, VE, is the voltage at the output terminals of the circuit when they are left open or disconnected from a load. Determining this value typically requires some circuit analysis with the laws of Ohm and Kirchhoff. So this one's a little bit more involved typically because we need to figure out what the output voltage would have been with the, all of the other sources and resistors, the original circuit. So you have to go back to that original circuit. Some gotcha that people tend to do is they do the first step, they take out all the sources, okay, they find the equivalent resistance, RE, check, and then they forget to put the sources back in to find VE. You got to put them back in to find VE. If you just have a bunch of resistors connected with no source, nothing happens. Okay, so it's not very interesting. So you need to do that. You need to put them back in and find VE. Something that is sort of embedded in this is that determining which are our output terminals is like the first step. Like you have to figure out what are your output terminals in the circuit before you can find an equivalent circuit, a Norton or a Thevinin equivalent circuit. Okay, so before we do an example, we'll do a Norton's theorem description because it's like the same exact thing, but with current sources. Okay. So, Norton's theorem. Given a linear network of voltage sources, current sources, and resistors, so same starting point, we got a network of a bunch of these circuit elements of voltage sources, current sources, and resistors. The behavior at the network's output terminals can be reproduced exactly by a single current source, i.e., so current source this time, instead of voltage source, in parallel, so that's different, with a resistor Re. So, slightly different, current and parallel instead of voltage and series, but very similar. So, the equivalent circuit has two quantities to determine, so it's just like before. Instead of VE and RE, we have IE and RE. The equivalent resistance RE is identical to that of Thevinin's theorem, so you do the same process. Set all the sources to 0, find the resistance between the two output terminals. The equivalent resistance, leaves, blah, blah, blah. So it leaves the equivalent current source, IE, to be determined. So we know how to find RE from the previous section. Now we need to find IE. The equivalent current source is the current through the output terminals of the circuit when they are shorted or connected by a wire. Determining this value typically requires some circuit analysis with Ohm's and Kirchhoff's laws. So let's imagine that I have a circuit that's in this box, okay? And it's got all kinds of sources and resistors in here. And it's got a couple of leads sticking out, right? These are the output terminals, okay? When we wanted to find VE said, okay, I've got a source, plus, minus, in series with the resistor, RE, VE, VE. And if I find RE and VE, I can replace this entire thing with this. Okay? That was what this is what Thevinin said. Thevinin said that.
Said you could replace the bottom with the top one?
It said you could replace this guy with like a whole bunch of resistors in here and sources and all kinds of stuff connected in all kinds of strange ways. You can replace all of that with this. Okay? Thevinin says that. Norton says, oh, okay, we can replace, we're going to take the same starting point here, and we can replace the same thing. I'll give it a little bit more space. Norton says, same starting point, but this time we're going to put in a current source. And we're not going to put it in series with a resistor, we're going to put it in parallel with the resistor. Okay, so Thevinin says you can go from there to there. Norton says you can go from there to there. So that is the idea. It's actually I'd say this is the first concept that people tend to have a lot of trouble with, Norton and Thevinin's theorems. I think that, yeah.
I was going to ask why might we really want to do this?
That's a good question. So, there are sort of layers to the response to that. On the sort of first layer we say, okay, you can take a complicated circuit and you can reproduce how it behaves with a very simple model. But you might say, well, if you already have to model the whole circuit in order to get the equivalent circuit, well, why does it matter? Like, it's like, sure, you've simplified it, but you had to do the complicated stuff first before you could get it simplified. And so the next layer to the response then is actually that we will often characterize complicated circuits with these values, especially the equivalent resistance value. The equivalent resistance value, and also the equivalent voltage and current sources sometimes. As we'll talk about in some of the lectures that follow this, they will tend to characterize an entire apparatus for us. Like, so, for instance, you guys are going to be in, well, some of you have been in the lab this week. You guys might have seen up on the shelf these power sources or power supplies, voltage supplies and current supplies. You can treat them, you can have them operate either way. So those supplies are, they can be characterized by an equivalent resistance and voltage. The inside of them is actually really complicated, okay? There's a lot going on inside. But at the output terminals, we can say the equivalent resistance of this source is X, and the equivalent voltage of this source is Y, even though the inside of the circuit is very complicated. So when you use that apparatus, when you use that instrument in your experiment, you don't have to go through and know the whole thing that's going on inside. You'll just be able to say, oh, it just looks like an equivalent voltage source with a resistance. So that's why practically it's very useful. We're able to characterize very complicated circuits, very complicated instruments that have a bunch of circuits inside them with these simple models, and they're pretty effective. So yeah, so that's a good question, and that's the main reason. So there are others, but I would say that's the sort of the one you guys are going to use it for the most. So yeah, and we're going to use a generalized version of this for more complicated systems too, to find the mathematical relationships between the input and the output. But that's not for months away. Okay, so converting, so the other thing is, if you notice that the equivalent resistance was the same, right? If you have a Thevinin or a Norton, you still have the same equivalent resistance. So it turns out you can convert between the two source models. So the equivalent resistance RE is identical in each and provides the following equation for converting between the two representations. And just so that I don't get it wrong, but it's almost impossible to get this wrong. It's VE equals RE times IE. So it looks like Ohm's law. So that's our bridge between these two models. So you could have done a Thevinin equivalent model and convert to a Norton just using this equation. Or you could go the other way. And I wanted to mention, well, actually no, let's do the example. I think we're ready for an example. What do you guys think?
Yep.
Yeah, let's do it. So, for the circuit shown, find a Thevinin and a Norton equivalent. Pretty simple circuit. And we are interested to find the Thevinin and Norton equivalents for it. So, it's kind of weird to want to simplify a very simple circuit. But even in this simple example, we have all of the interesting stuff happen in it. So, okay, so let's do Thevinin first. What's our first step? Yeah, so in order to find the equivalent resistance, we'll number it 1. Find equivalent resistance, RE. And let's go ahead and, this first time we're going to go through it more slowly, okay? And in the future we'll be able to go faster, but let's go through slowly. So we set the sources equal to 0, right? How many sources are in this circuit? There's only the one. So we set that to 0. It's a voltage source. So how do we set a voltage source to 0? We put a wire. We short it out. So let's redraw the circuit. Maybe later we won't need to redraw it, but for now let's redraw it with the sources set to 0. So we replace the source by a wire, the voltage source by a wire, and then we've got our R1 and our R2, and so R1, R2, and here are the output terminals, right? The out, I said there. So I want to know the resistance between these two terminals. How do I do that? I want to combine it down into one equivalent resistance. I don't want to have this parallel thing. I want one equivalent resistor there. What is my RE going to be? So I want to turn this into that with RE.
R1 times R2 over R1 plus R2.
Yeah, parallel resistors, so R1, R2 divided by R1 plus R2. Great. Notice that this is kind of something that is a little subtle. So these resistors, when we first looked at them, they were in series, right? Well, they were in series originally, but when we had the voltage source in there. But then we set the voltage source to 0, and we connected these two nodes, right? So both of the terminals are shared now for the resistors. This one isn't quite as obviously so, but if you follow the wire around, it's connected to the other end of the resistor. So this is another parallel situation. So they started out in series and they ended up in parallel in this. Sort of something to be watching out for. It's important to recognize how when you set the sources to 0, how that changes the circuit. Okay, great. So we're halfway there, right? We got RE. So now we want to find equivalent voltage source, VE. So we go back to our original circuit, right? Back to analyzing the original circuit. So we could go through and write down, we don't have a systematic approach yet, but we could go through and write down Ohm's law for R1, Ohm's law for R2. We could write Kirchhoff's current law at this node. We could do these nodes, but we would find that we would introduce a new variable that we don't care about. We could also look at Kirchhoff's voltage law around the loop, and we could solve for the output voltage. But before we do that, before we go down that whole route, is there a shortcut that we know already? Do we already learn how to analyze this circuit without having to go through the whole process. I know it was a long weekend. You guys forgot about a lot of stuff.
IE times RE.
No, so that was from earlier. So we can find Norton from Thevinin. You're right. So we can do that. But well, we're not quite there yet. We don't have Thevinin yet. We don't have VE yet. So we want to find VE. We want to find this output voltage, which is V out, without having to go through the whole circuit analysis. Is it a voltage divider? It's a voltage divider.
Yeah.
So that's a shortcut, right? We don't have to go through the whole process. We can say, oh, we've already analyzed the circuit. The circuit shows up a lot. We're just dividing voltage between these two resistors. So we already know how to solve that. We know that V out
Equals R out.
Yep, what's our R out in this case?
R2.
R2 divided by
R1 plus R2.
R1 plus R2. Great. And then we multiply that by what? Vs, the input. Great. And we also know that this is equal to, so we can also write that VE is equal to V out, right? That's why we found V out. So we've got our VE and we've got our RE. So we're done. It always looks the same. We can redraw it if we want. I mean, we could redraw our plus minus VE RE. We can redraw it, but it always looks the same, so it's kind of boring to redraw it over and over again. So now we can use this shortcut that we know RE is the same for the Norton equivalent, right? So we can find the Norton equivalent by just using this little shortcut here. But let's actually find it from scratch, because I think that it's good to go through and do them both in their entirety. Although, I mean, you could, depending on how I asked the test problem, you could potentially answer what's the Norton equivalent by finding the Thevinin equivalent and then converting it. But I might ask it in steps, and then you'd have to go through the steps to find the Norton. So let's do the Norton equivalent directly. It's very similar, very analogous, but it's worth understanding how to do both, okay? So I've got, this bar is going to kind of run through the middle, but originally when I wrote up this problem, I did the shortcut here. But I think it's worth going through. Okay, so step one for Norton equivalent, we got to find RE, right? But we already have RE. We already have RE. So we don't need to redo that. I mean, that's exact same. So what about finding IE? We gotta go back up here and look at this circuit. We want to find what current would run through. So let's go back up. This one's a little more subtle. The equivalent current source is the current through the output terminals of the circuit when they are shorted or connected by a wire. So we actually have to take this original circuit and then short this output connected by a wire. Okay? So let's redraw that. So we have our plus minus. We have our R1, our VS, And we've got our R2, and then we have our output terminals, right? So this is the original circuit. And then we're going to short out the output terminals. We're going to put a wire there. Okay? So if current is coming around here through R1, so say you turn this voltage source on, it starts to drive current through R1 here. What's going to happen when current reaches this node here, which is really this whole thing? What happens to the current? Is it going to go through R2 and through the wire? It's just going to go through the wire. It's way easier to just go through the wire. And assuming it's a perfect conductor, all of it will go through the wire, none of it will go through R2. Effectively, R2 will disappear from the dynamics of the circuit. You could actually solve for that by finding out what the resistance, doing a parallel equivalent resistance here too, where the resistance of the wire is 0. So you'd have R2 times 0 divided by R2 plus 0. So that's 0 over R2, or 0. Okay. So we've effectively shorted this out. That's what we say. We say shorting it out, meaning just circumventing a component by putting a wire across it. So our new circuit is just a voltage source and a resistor, and that's it, right? So the one current that's going to flow through this entire loop flows through R1, right? And we know the voltage across R1 is what? Yeah, it's just VS we called it. Yeah, just the input voltage. So we can use Ohm's law to find out what the current is that's running through R1, which is the current that's running through the short also, right? So IE is equal to, I will call it, is equal to IR1, right? It's the current through resistor R1. And Ohm's law says that V equals IR, or I is equal to V over R, right? So VS, well, in general it's equal to VR1 divided by R1, right? But VR1, voltage across R1, is just VS. So there we go. That's our solution. And we know we're done, so the question you might ask is, we don't have numbers in any of these problems. How do you know you're done? It's based on what is stated in the problem. So you're given this. So you're given VS, you're given R1, you're given R2. Assume that your inputs are always given. So sources are always given. Component parameter values like resistance, inductance, etc. Those are always given unless it's explicitly stated otherwise. Okay, so these are given quantities. So you want your solution to be in terms of given quantities, even if they're not given numerically. Okay, so R1, we just assume it's known. We would have to specify what that is if we wanted to find an actual equivalent voltage. But we know the formula for it now. We're solving for the formula for things. And that's what we care about most. And that's actually, I would say, a challenge people face in my classes is that I mostly don't give numbers for especially test problems, but even homework problems too. You just have to use the symbols to solve for things. And sometimes it takes a little bit of time getting used to. But I recommend you do that all the time. You don't have to just do that when there's no numbers given. Every time you're given, like, oh, this resistor is 5 ohms, just call that R1 or call that R2. Do the whole problem, and then at the very end, plug in the numbers. It's a really good practice. I know you've probably been told that over the years to do problems that way. But I would say now that you're getting into upper division engineering courses, it becomes even more important. Because oftentimes you're designing and you're not just solving, here's a circuit that exists. Maybe you're designing a circuit. You want to know what value should I choose for R1. You can't do that by plugging in a value, doing the whole problem, and then plugging in another value and then doing the whole problem. You want to solve it once and then plug in different values. And then have an idea of the functional relationship there too. Okay. And it's not as popular now, but engineers for many, many years loved making very, very complicated graphs. I don't know if you guys have seen some of the, you guys are in thermo right now, right? They're coming. Thermo is probably the place in engineering that they still remain extensively. But there's like multiple variables packed into one graph, and they're used for designing. And so these graphs are generated by understanding functional relationships. And yeah, so that's important. It's not as popular now because there's so many numerical tools to just program it in instead of having to worry about looking it up in a chart. But it's still useful to understand the idea. So okay, that's the equivalent Norton circuit. The equivalent Thevinin was found, and if we wanted to, we could go back and check that our we think that this is true, right? Converting between Thevinin and Norton equivalent. So VE should equal RE times IE. So let's check that. VE should equal RE times IE. So let's just plug in our VE on the left-hand side. So our VE was R2 over R1 plus R2 VS. R2 over R1 plus R2 VS. And that should be equal to RE, which is R1 R2 divided by R1 plus R2. Times IE, which is VS over R1. So the R1s cancel on this side, and you can see it immediately, right? They're equal. This implies that 1 equals 1, and we like that when that happens. So 1 should equal 1. Okay. Any questions on Norton and Thevinin equivalents? It's in your homework, so it's good that you're seeing this. Excellent. Okay. Onward and upward.